Hi everyone, today we are going to talk about an interesting concept called the mixture of experts. This is a concept that is used in many of the leading LLMs of the day. One example is the Mistral LLM, which uses this mixture of experts concepts. We will understand what the mixture of expert actually does, and then we will ask why it is useful and what are the challenges in getting a mixture of experts model to work. So what does the mixture of expert model do? In order to understand that, let's first start with an understanding of the transformer architecture, and I have previous videos which explain the attention mechanism and the transformer architecture, which you might find useful if you have not already followed them. I will link to those videos in the description below. But let's get a brief overview of the architecture in order to understand what the mixture of experts model does. The illustrated transformer from J. Alamar is one of my favorite resources, which I cite in almost every video that I do on large language models. This is the starting point to understanding large language models. And again, just as a 5-second primer, this is an example of a transformer model which is used for translating from French to English, and the idea is that we have the stack of encoder layers that an input sentence passes through in order to produce an output sentence. If you think about models like ChatGPT, the only difference is they are decoder only models and they don't have these encoders. But with that sort of aside, one of these encoders, the way that it works is that it is a self-attention layer which is followed by a feed-forward neural network. And just to understand a little more detail, we take each of these words, or what we call tokens, and then we transform them into these embeddings, which are sort of a huge vector, maybe like 768 or 1024 sized vectors, which represent each of these tokens, and then they pass through a self-attention layer to produce another set of vectors. And I have previous videos on how the self-attention layer works, which I will link in the description again. But today in this video, we will talk not about the self-attention layer, which we talk a lot about the self-attention layer in this channel, but in this video, we are going to talk instead about the feed-forward layer. So the feed-forward layer takes these sort of set of vectors, and then it passes it through another neural network layer, which is a fully connected neural network, a concept that you are very familiar with, and produces another set of vectors, which then again gets passed to the next sort of set of encoders, and you can see the encoders are stacked together. So that's the basic sort of setup here. Now, the feed-forward layer is something that most of you are familiar with. It is a fully connected neural network. I'll just show you a picture of the architecture here. So a feed-forward layer is something like this, where you have these, like each of these sort of elements of these vectors are these inputs, and then passes through a bunch of layers, and the idea is that they are all fully connected. So there is a connection from here to here, to every, so in layer 1, every sort of node in layer 1 has a connection to a previous node in layer 2. It is equivalent to the idea of a matrix multiplication. So you take a vector and you multiply it by a matrix and you get another vector, and so on and so forth. And that is the basic idea of a feed-forward layer. The problem is that this feed-forward layer often has a large number of parameters, because as you can see, the number of parameters is going to increase with the number of layers. Now let's come to, with that sort of example in mind and that sort of introduction, let's come to what is a mixture of experts. Let's try to understand this picture here, and this is a blog by Hugging Face. I will link to it in the description, one of the best sort of places to understand the mixture of experts model. So let's tear down the attention layer. So what happens in the attention layer is that we have all these tokens. Each token has an embedding. We go through the self-attention, and then we come to this feed-forward layer. And this is in the attention layer. In the mixture of experts, what we do is we have not one feed-forward layer, but a large number of feed-forward layers. So let's say we have 4 feed-forward layers here. and we choose one of these feed-forward layers or multiple ones. So each token passes through a different feed-forward layer. So the token more passes through one of the feed-forward layers, which is FFN2, and ignores all these other layers, and then is sort of added, the residual is added, and then finally we get to the next token. When we go to the next token parameters, it passes through another different feed-forward layer, not the one that the previous one passed through. And so that is the basic idea of the mixture of experts model, is that instead of having a single feed-forward layer, we have multiple feed-forward layers, and every token passes through a different feed-forward layer, or maybe a combination of feed-forward layers. It might pass through 1 and 2 and not through 3 and 4. So that is the mixture of experts model. The next question then is, how do we know which feed-forward layer to use for which token? And that is where the idea of a router comes in. A router is another model that produces sort of softmax scores, and we are using these scores to determine, well, the second one has the highest score here, and so we will now use the second feed-forward network. Then we take the next sort of embedding, and then we pass it through these layers, and then we pass it to the router. It passes through the first feed-forward layer because the first one has the largest sort of softmax score. And by doing that, we are sort of using this router as another layer, and then we are deciding based on the router score which feed-forward layer to pass it through. And so that is the basic idea of the mixture of experts model. Let me show you another illustration. Yeah, so I found this on Twitter, and I found this extremely useful from one of the sort of Twitter sort of threads, and this is the basic idea here. So to the left, you see a traditional transformer where it goes through this feed-forward layer, and then in the case of the mixture of experts, instead of the traditional feed-forward layer, it has this router, and it has selected these experts like the second and the fourth one, and it goes to these selected experts instead of these other layers which are redundant here. So the ones in red are redundant, they don't do anything. The ones in green are the ones that this particular embedding passes through. And that is the basic idea, and I find this illustration very useful. So that is the basic idea of the mixture of experts model. Now let me come to the second question, which is, why is this model useful? So think about this. This model is going to use less number of parameters during inference. So for example, let's talk about the Mixtral model. And the idea here is that there are 7 billion parameters, but there are also sort of more parameters because we have these 8 sort of mixture of experts. But the problem is, the advantage of the mixture of experts models is that the inference speed is like using a 12 billion model as opposed to a 14 billion model. Why is that? Because it computes less number of neurons, because it routes the embedding to one of the neurons, and these other 3, for example, are not used, which means that we use less number of parameters during inference. So that is the speed is like using a 12 billion model as opposed to a 14 billion model. So that is the advantage of the mixture of experts model. What is the disadvantage? The disadvantage is that you need a larger amount of memory. So we need to use a 47 billion parameters. If we are not using the mixture of expert concept, we would have used 7 billion parameters, but now we are using 47 billion parameters because we have like 8 mixture of experts, 8 of these experts in every layer, which means that we should have enough VRAM to hold all these 47 billion parameters, so it increases the memory requirement. So it increases the memory requirement of the model, but it allows us to sort of use sparsity to gain inference speed, which allows us to run a smaller model basically during inference. And that is the trade-off of the mixture of experts model. Let's now dive deeper into how the mixture of expert model works. The most important question is what does the router do? The router in its most naive implementation could be a sigmoid function, and it produces we define a matrix called WG, which is trained during the training of the network, and then we have this is the X is the embedding, and then it produce this softmax G sigma of X, and then we could take the maximum score from the softmax. But then we don't do that. Why? Because of an important problem, which is that of load balancing. If all our tokens were sent to the same expert or few of these experts will be trained really well, but the other experts won't be trained. So for example, if we keep sending all our tokens to FFN2, this expert is going to be trained very well, but these other ones are never going to be trained, and this is going to cause a lot of problems, because basically that is like training a single expert, and we won't get the advantage of the mixture of experts model. So how do we prevent this? And that is this load balancing is one of the biggest problems in deploying the mixture of experts model, and there are a bunch of different places where this is kind of fixed in the implementation. The first place where it's fixed is in calculating the router score. What do? We add a small noise. So in addition to this softmax, we add, so originally we were doing a softmax of XWG. Instead of doing that, we add a noise here. And then what the noise does is it allows us to explore rather than exploit. So because of this noise, sometimes we will choose a different expert and not number 2. And that's the first step that is done. The second idea is to keep the top k and not just the top 1, which means that for the top k values of the softmax, we we keep the scores and we make them the others minus infinity. And so what this allows us is that we are now doing a weighted average of the scores of the top k values instead of one value. So those are the two ways we can prevent one expert from getting trained and other experts from getting untrained. The other important thing here that we do, so this loss is the auxiliary loss. This loss here is another auxiliary loss we add, as I discussed before. So now the third important thing that we do is the idea of expert capacity. So each expert, we define the number of, for each expert, we say that we define the capacity of the expert. And the capacity basically says that the number of tokens that can be processed by the expert is limited by this expert capacity. If we exceed the expert capacity for one of the experts, we never send a token to that expert. And in fact, if we exceed the expert capacity for all the experts, then we don't even do anything, and we just send the residual to through the other branch. And so that is those are the basic problems that we, or the basic ways that we solve the problems for the mixture of experts model. So now you have a very good idea of how the mixture of experts model works, what are the advantages of the mixture of experts model, the trade-off it makes in terms of memory versus computation during inference, and you also understand the basic problems and how do we address those problems of load balancing in the mixture of experts model. Hope you enjoyed the video, and if you have any questions about how the mixture of experts model works, give me a comment in the video and I will do my best to explain it. As always, please like and subscribe my video so that I can keep making more videos about AI. Thank you.